now that we've kind of established what derivatives look like with multivariable functions, so when I have a function of several variables, how do derivatives work? What must I employ? I might need to use a chain rule. More fundamentally than that, though, what kind of derivatives do I have to employ? Partials, yes. So I have a function that's dependent on the values of several variables. So to tease out how the function itself changes, I have to kind of hold some things constant. The funny thing is, if you think about it, the way that we run, has anybody ever watched the show Mythbusters? Anybody ever heard of that show?
Yeah.
All right. As a statistician, Mythbusters makes me so happy because they talk about real things you have to consider. So very often, a lot of shows, they talk about controlling the variables. So you want to try to hold certain variables constant so you can see what effect the other variables have on the outcome, yes? So if you didn't hold certain variables constant, you might think one variable is doing something when it's actually this other thing, maybe the age of the person, if you're trying to study how a medication affects people. You guys kind of with me? Instead of the dosage. So maybe you're finding a result that's actually telling you how another variable is changing things. So controlling the variable is actually a statistical idea. But in our study, we have an output that's required, that's dependent on several inputs. So we want to do something very similar. We want to see, okay, how does this thing change if I hold one variable constant? Now what is the thing that kind of holds the total change? What have we investigated that kind of holds information about? Yes, the gradient. Because that I can say very specifically, what if I go this way? What's going to happen? And every time I talk about a different direction, I can go back and use the gradient. You guys all with me? And of course it makes sense because the gradient will include all of the various first partial derivatives depending on how many input variables there are. You guys. So most of the time we're dealing with z as a function of x and y, but as we saw in what I think is several people's favorite section, the chain rule section, we could have functions of like a lot of different variables, and those other variables could be functions of other variables, yes? And just freaking variables all the way down, yes? Not turtles, variables. Okay, I like it. Some of you guys get that. Okay. So, today what we're going to do, now that we've established, so analogous to Math 180, you first learn derivatives, and then you start doing stuff with those derivatives. And one of the very first things you did after you talked about higher derivatives was you started talking about maxes and mins. So we have seen several functions that have obvious maxes and mins when we graph them on Desmos 3D or something, yes? Yeah. You can imagine we've seen a function, a very easy one would be like an ellipsoid or something. It has a definite maximum, yes? In 2D, it was very simple to think about max and min because it was just left and right. It just had to be the highest point relative to looking up and down. In 3D, obviously, we have to talk about disks around it. Also, considering that we have partial derivatives, how the hell am I going to get critical numbers given that I have all these different partial derivatives to look at? You guys, does everybody understand the idea? So what's funny is we kind of mimic the progression of idea construction between 281 and 180. Just one is dealing with multivariables. So it's a little bit more. All right. So, yeah, that would be good. Good idea, Jeff. So if I'm given, this is 14.7, by the way. If I'm given function f of x, y, we say that a local max occurs at a point AB if f of x, y is less than or equal to f of AB. Now here's a little symbol, by the way. You ready? So real quick, this is just definition, yes? We're going to develop really good ways to identify, number one, critical points, and number two, how do I test those critical points to see if they're really maxes and mins? Because just to stop in the middle of this definition, was every critical number you found, bless you, critical point you found in Math 180, did it end up being a relative extreme? No, some of them were like, the most easy one is like where it just rests for a minute, right? Because, oh shit, or like we have right now, the economy sucks. Oh, maybe it's, oh, sorry. Okay. Little trick, like, oh, I'm gonna turn, no, I'm not. Shit. Okay, you guys kind of with me? All right, so this is just pure definition. It's not going to lead to a very practical methodology, but we have to lay down just the definition. So, given a function of x and y, a local max occurs at this point if f of x, y is always less than or equal to it near a, b. And of course, the operative word in that is near. This thing is doing a lot of heavy lifting, but the shit is near. So near would be a disk around the point AB. So unfortunately, even I didn't talk about this section the last time I taught 180. There's section 2.4 in 180, which talks about epsilon delta. If I say epsilon delta, does that mean anything to anybody?
No, you're speaking Greek to me.
Huh?
It's Greek to me.
That's so true.
Yes.
It's Greek even to Greece.
Didn't we use that when we were first starting to do those?
Yeah, I might have still talked about it a little bit. I think the last time I just didn't have enough time to do it, but it talks about, and so often in calculus, you talk about close, you talk about near, you talk about small steps, you talk about all this. That section was what defined what close meant. So epsilon and delta both were something greater than 0 that we normally consider as being very, very, very small. So this disk around AB would be like a disk of radius epsilon, greater than 0. And we normally consider that to be really stupid small, just a little disk around AB. So to be honest, to be a local maximum, you just have to beat out the points that are immediately around you. I can make epsilon, the radius of this disk, I can make it as small as I want it to be. So I can have, can you imagine, you've seen cosine and sine based z functions, where it looks like this egg carton. Have I shown you that? I think I've shown you that at least once. So you have so many local maximums, and I can create the period of it so that it has a local maximums like crazy often. But if all right, I think you guys maybe get the idea. Okay. So again, this is a definition. It's not a methodology. Thank the gods. Blah blah blah. Yeah. Okay. And then I could do the same thing if I wanted to put min here. I would just make this go the other way. So to be a maximum, you have to beat out all of the other points near you. To be a minimum, you have to beat out the race for the bottom, all the other points around you. Okay. I like it. Hey, Mikey. Now, real quick, if I have a plane, the plane z equals 7. Does it have a local maximum? Can somebody describe the plane z equals 7 for me?
It's like a ceiling.
It's a ceiling. I love it. And what's a really good ceiling normally do? Unless you have a really funky old house, it maintains the same distance above the floor, yes? You might have a funky house where it does this kind of thing. Yeah, okay. You with me? So this ceiling, for example, considering everything went well with the foundation of this building, the ceiling should be the same distance from the floor as you move away. So that's like z equals 7. That is 7 units away from the xy plane. Is that cool? That's the best way to describe that plane. Does it have a local maximum?
No. Nowhere and everywhere at the same time.
So the official answer is yes. In fact, it achieves its local maximum everywhere. Does it have a local minimum?
Yeah.
Yes, it achieves its local minimum everywhere. Yeah. So could I have several local maximums? Could I have several local minimums? Yes. If you just keep reducing the amplitude, won't you still have the same number of maximums and minimums?
Yeah.
Now, if you make the amplitude 0, it still has so the whole reason that that's true is because of the equal to in that part right there. Now, real quick, you all agree with me that the local max, local min for a flat surface like z equals 7 is sort of a silly thing. It's kind of a trivial solution, which is we call like, if I make all the variables 0, I get 0. Ooh, good job, you know. So the trivial solution is not very interesting, but it does match the definition. All right, let me stop for a minute. So how often are we going to be analyzing planes that are flat, parallel to the xy? Not. Most often going to be analyzing, of course, unfortunately for everybody, funky ass ceilings, which got some personality to it. Okay. You guys all good? Okay, so definition. Now let's talk about where Jeff forgot his glasses. Practical ways to do this. And the first thing they have to figure out is, how do I find critical numbers in our new multi-variable world? And interestingly enough, in Calc 1, you actually find critical numbers based on a theorem that kind of talks about it the other way at first. So what do I mean by that? If f has a local extrema at AB, then f of x and f of y exist at AB, and fxab equals fyab equals 0. Now that, sorry. So if f has a local max or local min at some point AB, then fx and fy both exist. And they both equal 0. Let's see if they give you. Yeah, okay. Oh. Yeah, that's what I mean. Not then, but and. This is the then. There we go. So if f has a local extrema and f of x and f of y exist at AB, then f of x AB equals f of y AB equals 0. Now real quick, how did you find the critical points in Math 180?
Set the derivative equal to 0.
Set the derivative equal to 0 or where it was undefined. Yes? Because again, is this differentiable at that point there? Is that function differentiable here? Why not? It's a cusp. Be more technical. Why is that not differentiable there?
It's discontinuous.
What's discontinuous? The function is not discontinuous there, yes? I don't have to lift my pen to draw that.
There's an asymptote.
What has an asymptote there?
The function?
Nope, the function's fine there. The function has no problem there. It's continuous.
There's no like tangent line there. Slope goes to infinity at both sides.
Sort of. It's positive infinity on one side, negative infinity on the other side. Yeah.
Yeah.
So that's a
As
So a really good definition of differentiability at a point is the derivative itself continuous at that point. So the most basic function that's not differentiable at a point is the absolute value function, right? And that's the most basic kink. No shaming this poor little dude. So at the point 0, 0, if I have y equals absolute value of x, I haven't put a scale there, but you'll know what it is. What's the slope to the left of 0? Negative 1. What's the slope at the right of 0? So if I graph the derivative of this function, it's going to look like this. Yes? So is the derivative itself continuous? So the best definition of differentiability at a point is the derivative itself continuous? Because when you take a derivative, you're constructing a new function. You guys go with me? People normally get continuity. Differentiability is weird, but if you just look at it like that, not so bad. Okay. Why did I go down that? I don't know. Oh yeah, because this one says if f has a local extrema and, it's like a dumbass I put then first, and the two exist, then v equals 0. There could be a function in 3D that effectively does this thing from all directions, yes? And that would still be a local extrema, it just, they wouldn't exist. So I can still find my critical points according to where f of x and f of y are both 0. And by the way, notice it says, in my fantastic handwriting that's only gotten better after the break, it says that they both have to be 0. Yes? Not just one of them, they both must be 0. Okay, I love it. You know, like, great, Jeff. Whatever, dude. So, what's the method then to find the critical points?
See if they're not equal to 0 at those points.
Well, no. So, figure out fx, figure out fy, set them equal to 0, or see where they are on the way. So for the exact same thing, the exact same way we did in Math 180. Now, I need you to see this. If we do that, we're doing the kind of the reverse of what this says, yes? Doesn't this theorem say if f has a local extrema, then these two things are true? You with me? So if those two things, I think this is what you're thinking, maybe the logic of it. If those things are not true, then f does not have a local extrema there. If these things are true, does it have to have a local extrema there? No, that's the key. That's why the list of critical numbers, the list of potential extrema locations, was often bigger than the actual number of extrema. You had to check them. You couldn't just say, well, there you go, I'm done. No, you had to check them to see, is it just tricking me? Or is it actually doing something turning? Yes? Okay. So, obviously, this is the one nice thing here is there's a direct comparison to make with Math 180. The thing you should totally understand by now, because you've been living in this class for a while, is every damn thing is going to be a little harder. Because we have all these multiple directions to look at and so forth, yes? Okay. So let's give this a try. In fact, yeah, maybe I could do that. Yeah, why not? Well, let's see. All right, let's do this. Well, let me just make one up out of nowhere. No, that could be crazy. I'm going to give you this. Yeah, why not? Screw it. You're going to see a few things earlier than I want you to. Oh, yeah. Well, we didn't quite make it through 14 for exam 2, so everything got pushed forward a bit. So I want to try a couple of these out with you. Let's see. Let me see, which one's not too freaky? Yeah. Can you guys do part B? So what do I mean by that? What's the steps? What's the first thing you want to get? The partials, the first partials. And then you want to set them equal to, or see where they are. Just go.
Wait, see where they are on the what side?
Set them equal to 0, and or see where they're undefined.
Oh, okay.
Yeah. start to catch up to you guys. Now, this one's pretty good. That's why I want to start with this one, because it's got pretty straightforward first partials. The real key thing here. This one's easy. How many variables does fx depend on? One. Fy. One. Now, if you look at some of the other ones and start getting these cross products of x and y and so forth, those are going to get trickier. There's going to be like systems of equations you're going to have to solve. Yay! This one's really straightforward. The key to remember is both partials must be 0 at the same time. So whatever point you claim is a critical point, better make both partials 0. The funny thing about the undefined part is at least one of them has to be undefined. So we're not hitting an undefined yet. So let's just look at this. So what makes this 0?
1.
And what makes this 0? Yeah, 1/4. Is that cool? So what point has both of those true? Holy shit. So this one's nice. There's one distinct critical point, and you just have to construct it based on those. Now, are they always going to be like that? Oh, hell no. Is everybody with me so far? So that one's a nice one to start with. Very straightforward. You can just set them equal to 0, construct the point. So try part it.
Just to confirm, so if there was like two values for x and one value for y, you'd have just the two kind of possible it's all possible permutations of the values of x and y. There would be possible.
Yes. So for example, if our fy was quadratic and all, you would have two separate answers, and then you would combine them with the x.
Another quick question. What is the symbol that you define that point as?
Oh, CP.
Okay.
Sorry. Yeah. I know. Oh, anybody else come in and not get their test back? I don't want to carry it around. Okay. Who else? Oh. Yeah. I'm sorry.
My bad.
What's up? Ah, sure. Ah, okay, let's take a look. Okay. It looks alright. Let's see. So what do you guys get for fx?
2x equals 2xy.
Yeah, 2x minus 2xy. I like it. And fy?
4y minus x squared.
Kick ass. Now, this one's kind of tricky. If you set fx equal to 0, what do you get? If you
Isn't it y equals
do it again. Oh, gotta be careful. So if I factor this thing, I get that, yes? So either y equals 1 or
x equals 0?
so far so good? I don't know. Now, if you look at fy, if you set this equal to 0, you get like y equal to 1/4 x squared, yes? Is that, you guys see that? Oh, set equal to 0. So, it has to make both partials 0, yes? So y equals 1 makes the first partial 0, x equals 0 makes the first partial 0, yes? does y equals 1 make the second partial? Or let me say it this way. If I set y equal to 1 here, what would x have to be? 2. Or negative 2. I like it. So would the point 2, 1. So if you want to check yourself. With the point 2, 1, would that make this 0? Yes, because it doesn't matter what x is. If y is 1, that's 0, yes? Does 2, 1 make this 0?
Yeah.
Yes, because it's on this graph, yeah? Which makes that 0. Let me stop for a minute. Do you guys get the idea? This is a still semi-straightforward example. It's not really a system of equations. I got 2 definitive answers, numbers, from one partial, and now I just have to kind of use them in the other. Is everybody with me so far? And do you see how you can check yourself when you're starting to understand this? Whenever you say that something is a critical point, plug it into both partials. Make sure it actually makes them both 0. Or undefined, if that's where they came from. And what if x is 0? Then y is 0, yes? So the point 0, 0 is a critical point. And the points 2, 1 and negative 2, 1 are critical points. Those are locations of possible mins and maxes, extreme. I love it. You guys with me? Do they all have to be actual locations of mins and maxes? No. Again, could be a little trick. Yes? In fact, now that we've got multiple directions to consider, do you remember the saddle points? We talked about saddle points. So one way it looks like this, and the other way it looks like this. So that little point is freaky as shit, because according to this way, it's a min, but according to this way, it's a max. So obviously that is neither. And it actually is a specific designation given to anything in that situation. We call it a saddle point. This is going up one way and down the other way. So I can put my legs there and have the thing come up. Yeah, okay. You guys with me? Literally, it's a saddle. Okay. How are you guys feeling so far? I mean, obviously this is a little harder than 180 was, but not that much harder. At least not yet. All right, try out part C. Yeah, that one a little bit. Okay. All right. Let's see if anybody gets this one. This is a special case. What do you guys get for FX? That kicks ass. FY?
Negative sign.
Cool. Now, whatever point that would be the answer for the critical point must make both of those 0 at the same time. Can the variable x make either one of them 0?
No.
I cannot raise a power, if something is not 0 already to a power, make it 0. You with me? Bless you. If something makes fx 0, does it also make fy 0?
No.
Because cosine and sine are offset by 90 degrees, or pi over 2, yeah? Do you guys see the idea? If you find, so what makes fx 0?
Y plus or minus 1.
Oh,
I
Pi over 2
Radians.
plus or minus
Pi. Okay.
pi k. Pi k. You guys remember that? I love it, right? Because of course there's an infinite number of things. What makes fy 0?
Pi. Or 0.
This will be just plus or minus pi k. Is that cool? 0 plus or minus pi k. Is that cool? So if I'm on the x-axis, sine is 0. If I'm on the y-axis, cosine is 0. That's basically what those two things say. And to get from one side of the axis to the other, just go by pi over 2. Is that cool? That's what both of those say. Can those both be true at the same time?
No.
No. So what are the critical points?
Does not.
There are none. It's got no critical points.
Why is it pi k and not 3 pi over 2?
For the second one,
For the y equals,
this guy?
no, the other one.
Oh, this one.
Mhm.
Oh, okay. Okay, you ready? Pi over 2 definitely works, yes? Pi over 2 makes cosine 0. If I add pi to pi over 2, what's 1 pi plus half a pi? That's 3 halves of a pi, correct? That's 3 pi over 2, so I caught that. If I do pi over 2 plus or minus any multiple of pi, I will capture all the half. So I caught that one too. You're correct. But that is in that list. Okay, I like it. You guys all with me? Hopefully you remember that from trigonometry. Really?
No.
Oh, that's right. Some of us somehow got to this point without much trouble. So very quickly. Let me see. Very quickly. You all know that sine 0 is 0, yes? Okay. How far do I have to go until sine is 0 again?
180.
Yeah. Well, 180, which is also known as pi. Because this is radians, because they didn't put degrees. Yes. When you don't see a degree symbol, it must be radians. Right? All right. You guys with me? So stay in the units I used. Is everybody with me? So, what makes cosine 0? What's the most fundamental thing that makes cosine 0? Pi over 2. Right? So sine loves it here because sine likes y. Cosine likes x, so sine hates it here. Yes? So if you think of it as a little turtle, it's got its head fully pulled in because it doesn't like it there. I don't know. You guys would talk this. How far until cosine is 0 again? Well, again, pi away. So if I add, and then how far again until pi is 0, until cosine is 0 again? Another pi. What about going backwards? I can go backwards, I can go forward. So if I just add or subtract any natural number multiple of pi, I'll get to another place where cosine is 0. The same idea with sine, just offset by 90 degrees. So it starts at 0. Is everybody with me? Does that make sense?
Yeah.
Roughly, I mean, that was like a week's worth of trig lectures condensed to less than a minute. So, all right. All right, where was I? Oh, so this is an example of a function that has no critical numbers. Therefore, it has no. Let's graph it. Let's see what this thing looks like. Let's all sit here while Jeff tries to remember his login.
I think it had 3 in it.
Huh?
I think it had 3 in it.
It's got a 3 in it?
Yeah, it might have 3.
It's got a multiple of 3 in it, I'll tell you that. That's all you're going to get out of me, by the way. A long time ago, my password for everything, it's not true anymore, so don't try it. It was, what is it? What is it? Oh, yeah. All right, so let's try to graph this thing real quick. I didn't graph this earlier, so I'm not even exactly sure what it's going to look like. Come back down. Ooh. Stop! Good Lord. Yeah, it just flattens out. That's really freaky looking. So it's got nowhere. So this is the e to the x. Yeah, let me do this. Sorry. This is the e to the x part, yes? Do you see that? That's e to the x. E to the x has no maxes or mins, yes? Because it has no turning points. You with me? And then if I turn the sucker around, there's the cosine part, yes? You can do this with yourself, with Desmos on your own time too. How are you not lining up? Oh, because you got off this kilter for some reason. There we go. But yeah, there's the cosine part. It's got no hills or valleys. So it's got no maxes or mins. Okay. I'm losing people. Okay. I'm against Desmos. Okay, I'm sorry. So coming back to this. Real quick, let's do these together here, in the interest of time. What's fx for part D?
2x.
Good. And what's fy? Good. Now, one way you can do this, two things have to be true to be a critical point if there's nothing that's undefined. Fx has to equal fy, and they both have to be 0, correct? Let me say this again. Two distinct things must be true. Fx must equal fy, and they both must be 0. So, this problem is not going to necessarily happen, but you could either set each one equal to 0 and then see when they match, or you can set them equal to each other and see if those things make them 0. When I have two things that have to happen, and they're not dependent on each other, I can make either one of them happen first and then check to see if the other one happens. Did anything I just say make sense? What two things have to happen? First partials have to be equal, and they have to be 0. So I can either see, and the way we've been doing it so far was I was setting them equal to 0 and then seeing where they match. You could instead set them equal to each other and then see if those points make them 0. Now in this case, let's see how far it gets us. I don't think this is one we have to worry about too much. If I set each of them equal to 0, what do I end up with? You guys notice anything?
Y equals 1/2 x.
Yeah, for each of them, yes? If I set them equal to each other, you would have gotten a tautology. I think, let's see, 6x equals 12y, you would have gotten, y equals 1/2 x. So if you would have set them both equal to each other, you would have gotten the same thing. So y equals 1/2 x. Does that make fx, does every point, now I really want you guys with me. You're going to get this sometimes. So far we've gotten distinct points, yes?
Is this one is the equal 7? Or
No, definitely not. It's got some curviness to it because I can see that.
Because like you said, like they're all of them are like what is it? You said all of them have the extrema, like it's all.
Oh, if I had a plane,
Yeah.
if I had like z equals 7, then every point is a local max and every point is a local min.
Is it gonna be like that? Like every
No. I can tell from the fxy. It's definitely got some curvature to it because it's got the squares and stuff. You with me?
Yeah.
So no, it's not going to be that. But we've seen examples. Remember when we were trying to get the limit and we saw the pathway where if we went down this, it was always at the same level? And then when we went to another way, it was always at the same. I don't know if you guys remember that. For some reason, it really sticks in my head. And you're like, I don't pay attention to you, Jeff. All right. So, every point on the line y equals 1/2 x, what does it do to fx? I mean, if I made y equal 1/2 x, wouldn't this be 0? Yes?
Yeah.
If I, what's the matter? So, try it. Be all right? What happened? If I make, here's fx, and I got y equals 1/2 x. What do I get if I make y equal 1/2 x in that? 2x minus 4 times 1/2 x equals 2x minus 2x is 0. So let me ask you again. And by the way, are you guys, when I plug this in, how many points did I just plug in?
Everything on the
Infinite number, everything on that line. Every point. In fact, give me a number on that line. Any number on that line. Any point on that line. Sorry. Specific point. Give me a point on the line y equals 1/2 x. How do you do that? Pick an x. Give me an x.
7,
What?
8.
Oh, careful. So if you say this is 7, if x is 7, what must y be so it's on that line? 7/2, yes? You guys with me? That was interesting. You guys have been there a bit. What do you get when you plug that? Plug it in. I'll wait. Plug that point into fx. I need you to get this. So, because you're going to get this a lot. Do you guys understand how when I take partials, I end up very often with functions of multivariable. I still end up with something that's got x's and y's in it, correct? So I'm going to end up with this situation a lot. And when I say I mean you. I'm going to be here near you when it happens, but you're going to be doing it. So what that means is any point on y equals 1/2 x makes fx 0. Does it also make fy 0 at the same time? In the same way, yes? You guys with me? So what are the critical points for this function?
What if that line?
Every point, you basically said it, but I want you to really say it.
Any point in the line y equals 1/2 x.
Yeah, every point on y equals 1/2 x. Every point on that line is a critical point. So real quick, well, let's graph this. When I say let's graph this, I mean you watch me graph it. So everybody got that? Every point on the line is a critical point. All right, let's see, what was it? Get out of there. X squared, no, plus, was it plus 4y squared?
Yeah.
Do it.
Plus 4xy.
Minus 4xy plus 2, yes, the infamous plus 2. Now, there we go. So guess what line that is? You can do it. Oh, there it is, yeah. So the y equals 1/2 x line makes a trench. So at every point on that line, it's actually on a parabola, yes? So I'm going to come back to this problem, especially now that we graphed this, because you could see since we graphed it, is that the location of a max or a min? The min, yeah. You guys with me? And do you guys remember in 1/8? Okay, let me make sure. Is everybody with what just happened? At every, see, I'm watching, so don't lie to me. Don't trip me up. At every point on y equals 1/2 x, that's what that line is, yes? It's in a valley on the surface, on the fxy. At any specific point, it's the vertex of a parabolic cross section. Is that okay to say? So at each point, you can think of it as math 180, because then it's just if I just take a point and slice it, now I'm in math 180. It's a min. Move to the next point. It's a min, because again, it's cross section slice. It's a parabola. Yes. So that's going all the way down the center. So every point on that line is a minimum. That's how that happens. Are you guys at all with me? Sure, Joe. Okay. All right. Okay. You sure you're with me? You still looked, because you answered it like this. Okay. This is new. That's what I knew it was going to look like. Because, ooh, look at me, I'm special. No, because it had to look like this. This is the only way that it could be relative. Either it had to look like this or like this repeated. Yes? So that along that trench, I keep thinking about freaking Star Wars or whatever, I'm sorry. Along that trench, it has to either be continuously the top of a hill or the bottom of a valley. It just has to be. Okay. Maybe. try this. Time. Okay. How far do I want to make it? Oh yeah, that's right. Okay, good. We can do it. We can do it. My goal is to let us out a little early today. Just to kind of ease us back into things. And you're all like, this is not easy, this. Also because I have a lot to do.
Can I ask a dumb question?
Always.
The critical points are the extrema?
Oh, you're right.
Critical points are possible locations of extreme.
Like all the time.
Because y equals 1/2 x, so it's not as long.
Well, because we graphed it, we could then see it was a minimum. If I had not graphed it, we would have no clue. Yeah. Yes.
For this one over here, and since they put A in the same pair, I would do that so one was
That's part of it. Yeah, this one's trippy. Okay, let me catch up to you because this one's a little tricky. What do you guys get for fx?
3y minus 2x
Y minus half
y squared.
Minus y squared, I like it. And then fy.
3x minus 2x squared minus 2xy.
Yeah, now, this is where setting them equal to each other is not a bad way to go. Because if you try to set either of them equal to 0, it doesn't really get you anywhere. I don't know if anybody tried doing that. This is what I was prepping you for, was this one really. The part D, you could have done it either way, and it would have gotten you y equal 1/2 x. This one, can you see what immediately is nice if you set them equal to each other? And I really want to make sure you guys understand why I'm doing that. Again, they must equal each other, and they must both be 0. I don't care which one you make happen first. They just both have to happen. So in this case, we're like, screw making them each 0. Let me set them equal to each other and then see where they're 0. Yes? So if I set them equal to each other, what immediately happens? Yeah, the 2xy cancels. And then I get, let me just go ahead, since I'm running out of room here. If I factor this a bit, what I have left, so this dies and this dies, yes? You get something that looks very, symmetric. Can you guys see an obvious answer to where these are equal to each other? Yeah, if x equals y equals 0. Yes? If x equals y, those are equal to each other, yes? If x equals y equals 0, those are both 0. You guys with me? So one critical point is 0, 0. Yeah, we'll do it. Does anyone see another critical point? What about 3? Sorry.
3 minus 3 is 0.
That's true.
X equals
3
y.
minus 3 is 0.
X equals y equals 3.
Yeah. Oh.
That's what I was.
So how'd you see that? Zach?
X equals y equals 3.
X equals, do it again?
X
I'm sorry, I thought you said something else. So let's see. If I make those both 3, like several of you guys have told me, then both of these equal 0, but did both of these equal 0? No. Now obviously if x and y are both 0, these are both 0. Is that cool? Because every term has an x or a y in it. So if x and y are both 0, 0, 0 is definitely a critical point. Because it makes both fx and fy 0. Does the point 3, 3 make both of these 0?
No.
So you checked it out? Okay. Trust you guys. So 9 minus 18 minus 9. No good. 9 minus 9 minus 18. No good. Okay. I like it. Are there other critical points though?
This is 3, 0, and 0, 3, I think.
Do it again.
Oh, never mind. That
Oh.
doesn't work.
Let's get excited for a second.
If x is 3,
What if x is 0 and y is 3? Is that what you said?
Yeah.
Alright, let's see. If x is 0 and y is 3, 9 minus 9. Yes? And then if x is 0, y is 3, 0. You with me? So what's another point that works?
3, 0.
3, 0. For the same reason, reverse. Yes? Now, real quick. That's probably the trippiest problem, even trippier than F. And some of you guys are looking at part F. I scratched it out just because I wanted some more room. This one is excessively trippy. Because if you make x 0, then this side is 0. And then how do you make this side 0 if y is 3? Now that works for this, but then you have to go back to the original, yes? So if you make both of them 3, it does make this zeros, but that's not what fx and fy were. This is after some algebra. Does that make sense? So you always want to go back, especially with trippy ones like this. Whatever point you think work, you need to go back to the original fx and fy and see if it makes them 0. So again, whatever you think the critical point is, how do you check yourself? Go back, make sure it actually makes each of them 0 on their own. Yeah.
would 1, 1 work?
Let's see. Would 1, 1 work? 3 minus 2 minus 1, 0. 3 minus 1 minus 2, 0. So there are more answers in here somewhere.
But then they don't equal to 0. But
True, and it's because we canceled this piece out.
okay.
Yeah. Now, real quick, let me see if you guys are with me on this. What if I made, let me write this down here. Let me see, hold on. Y equal to, 3 minus x.
Then x equals 3.
What happens then?
X equals 3.
If y is 3 minus x, this is 3 minus x times 3 minus 3 minus x. This is 3 minus x times x, which is this side, yes? So this makes both of these equal to each other. But does every point on this line make fx and fy 0? Now, let me stop for a minute. Is this the trippiest one yet? Yes. Have the other ones been relatively not that bad?
Yeah.
Okay. What class are we in? Calc 3. So this is what you should expect. Now, with that said, this kind of thing is not going to happen a lot, but it will happen. Okay. So how do I check if every point on here? And what's one point on here? Isn't one point on here 3, 0? Isn't that what we found? Isn't 0, 3 also on here? No. So instead of checking an infinite number of points, how do I check to make sure this makes fx and fy 0? Just go back to fx and replace y with 3 minus x, yeah? Do you guys see what I'm saying? If I go back to fx and replace y with 3 minus x, that looks exciting. Make sure I put it in there right. Yes, sir.
Why did you decide to write it as y equals 3 minus x?
Instead of what?
Because it makes them equal to each other.
Yeah.
Can you show the intermediate steps? How you
Yeah. If I make y equal to 3 minus x,
Okay.
I happen to also make this become x. So one thing you
okay.
could do when you have an equation like this is try to set this. Setting y equal to x works, yes? Well, then try y equal to 3 minus x for the same reason. And the fact that this is kind of symmetric, that kind of thing is going to work. Now, how often is something like this going to happen? Not very. You guys with me? And is spending too much time on this problem, but we'll be okay. This does not look like it's going to pan out. Yes?
9 minus 3x.
Yeah, 9 minus 3x minus 6x plus 2x squared minus 9 plus 6x minus x squared. So this becomes 3x. Oh, let's see. Sorry. Negative 9x. Yeah, so negative 3x plus x squared. And I want that to be 0. So either x has to be 0 or x has to be 3. Yes?
What happened with negative 9?
So again,
What happened with negative 9?
9 minus 9.
Oh.
Yeah. I didn't like the look of them, so I threw them out. Alright, that's enough, because we're not going to see a ton like this. I don't want to overemphasize this problem, because then you're expecting every problem to be like this. So, by the way, real quick, just put a bow on this. We figured out just now, that not everything on this line works, just the points that we found here work. So these are my critical points. Now, let's go with the problem a little bit. Let's go. I just want to show you a freaky one, just to show you some of the logic you have to employ in a couple of problems. The next thing is, I don't want to use the definition to freaking tell if these are local maxes or local mins, because I don't want to check every possible point within a disk. No. So in 180, we had two methods to tell if a critical point was a relative extrema or not. We could use the number line method, remember this? And that was effectively doing what I just said, but in Math 180, how many directions could you move? 2! So I can make a number line and just see, oh, it's going up that way, it's going down this way, so it must be a minimum. Yes, do you guys remember that? It's going down and going up. Oh, it's a minimum. Now, for us, we'd have to check everything as I rotate. So the other way that you did it in Math 180 was the second derivative test. Concavity, yes? If it's a critical point and is concave down through it, then obviously that is the location of a max. And then alternately concave up through a critical point, that's a min. Yes? That is fantastic. That is just so simple. So you have to have a critical point, and if it's concave up through it, that's a min. If it's concave down through it, that's a max. Of course, could it be inconclusive? Hell yes. Right? I don't know if you guys remember that. This is a while back. Okay. So here's the tricky thing. Obviously, the second derivative test in Math 2A1 must look worse. Why? How many second derivatives are there? There's like 3 main ones, because Clause's theorem says that one of them is like equal to another one, yes? So if I have fx and fy, I then have fxx, fyy, and fxy, fyx, which should be the same for most of the functions we use, yes? You guys all with me? Yes. It would be very tripedelic functions that would not match Clause's theorem. Whenever I see that, I think of Clarice from Science of Lines. Sorry, that's not what that is. So here's the theorem, just in your face. If I have a critical point, AB, that is what I calculate. Now, let me see if I can get you guys on my side about this. So everybody see what goes into calculating D, right? It's fxx, fyy. So fxx is how fx is changing as I move along the x-axis. So if that is, now look at part A. Let's see if you guys are with me on this. That's how part A says, if D is itself greater than 0, and fxx is greater than 0, meaning it's concave up as they move along the x in the x direction, it's a relative min. Now, real quick, bless you. You guys with me? Think about this for a second. Do you see how f of x and fyy are multiplying by each other? Do you see how fxy is squared? So I'm subtracting a positive number, correct? So to calculate big ass D, I'm always subtracting a positive number. Or maybe 0 if it happens to be 0. You guys with me? Therefore, if it is positive, and this piece is positive, what else is this saying? What is it saying about this piece? What must be true about this? If that's positive, and this whole thing is positive, what can that not be? Can't be negative. Okay, so inherent in part A, if D itself is positive, and you just check to see if fxx is positive, you also show that fyy is positive. So it's up this way, and it's up this way, so of course what should be happening here? A freaking min! If it's concave up this way, and it's concave up this way, this must be a min, yes?
Yeah.
I'm trying to point to the vertex of my arms, yes? Okay. You guys with me? I won't do an eat one. Some of you guys, okay. Sorry. Why did I say that? I don't want to think about any of that. Okay. Is everybody with me so far? Does that make some sense? Now what I definitely don't have time for, which is unfortunate, is this kind of looks like a determinant. What was for the quadratic formula? What's inside of the square root?
It's
Plus or minus 2ab.
b squared minus 4ac.
B squared minus 4ac. Now if I turn that around and I made 4a like d, that would be dc minus b squared, yes? Isn't this dc? Isn't this something something minus something squared?
Yeah.
So the proof of this, now what I just said I think is good enough for us, especially if you're with me. If fxx is positive and fyy is positive, there's a min here. And that's what happens for part A. Part B, if d is greater than 0 and f of x is negative, what's got to be true about fyy so that it actually comes out positive? If fxx is negative, and I'm subtracting something that is at least 0, what's the only thing that's going to make d positive? What's got to be true about fyy then? It's got to be negative. So if I'm concave down this way, and I'm concave down this way, then this is obviously a
Max.
googly face. No, this is obviously a max. Yes. You guys with me?
Yeah.
Okay. So there's an entire proof of this that uses Taylor series, uses quadratic approximations that leads to a quadratic formula that gives you this thing. Does that sound? That sounds horrific. But I just want to lay it out there. There is a proof, and I'm not going to take us through it. And I'm sorry if you're really upset about that. You can just be upset somewhere. Okay, what about part C? That says the result of this is negative. If the result of this is negative, then either these two are opposite signs. Yes? Either they're up, so it's like up one way and down the other way. That's obviously a saddle point then.
Or it's equal to 0.
Or one of them is 0, which means in one direction or the other direction is flat. Yes? And in that case, I have a saddle point. And the only way that no conclusion can be drawn is if d equals 0. And if no conclusion can be drawn, that sucks. So let's try a problem now. So this one was from part A. What was our critical points from part A?
2, 1, 0, 0.
Where did I put them? There they
That's
are.
less than 0.
Plus or minus 2, 1,
No, it's not. Yes.
and 0, 0. So, what do you have to calculate in order to use this? All of the second partials, yes? Except for fyx, because that's the same as fxy. By the way, real quick, do you see how that's why that's squared? Because it's really fxy ab times fyx ab. Since those are equal, it's just that thing squared. Yes? Can you take a moment and calculate, look back at the first problem, because it's the first problem again, right? Take fx and calculate fxx and fxy. Take fy and calculate fyy. I'll wait. So everybody with me? So this is the first problem on this paper. So take fx, calculate its second derivatives. Take fy, calculate fyy. Okay. I did all this somewhere, and I have no idea where to put them. Bless you, bless you, bless you. Oh, it's right here. No. It's not this isn't too evil. Just to put up here what these were again. fx was, and fy was. Okay, so that was from the problem dealing with this guy. So what do you guys get for fxx?
2 minus 2y.
Yes. What's xy?
Negative 2x.
Yeah, negative 2x. And what's fyy?
Four.
4. I apologize for that. So what's nice is fyy is 4 no matter what the hell. Yes? So that's kind of nice. So now I take each critical point one at a time and I just plug it in. Yes? So if I take the point 2, 1, what is fxx at 2, 1?
0.
Yeah, 2 minus 2 is 0. Times, who cares about fyy? And what's fxy at 2, 1? Oh yeah, squared, right?
Yeah. So it'll be 6.
Yeah, so it'll be, if you plug a 2 in, you get negative 4. Squared is 16. So you get 16. And that is greater than 0, yes? So d is greater than 0. And fxx,
Is it?
How is that?
wait, what happened? Oh, it's negative 16.
Yeah.
Sorry, less than 0. There we go. D is less than 0, that's a saddle point. Okay. But, oh, okay. This is beautiful. This is really bad that I made the mistake because this is exactly where I wanted to say this. Remember how we said a minute ago that the only way that that condition C could work is if either fxx and fyy were different signs or one of them was 0. So that's exactly what happened here. Okay.
So if one of them is 0, then it's always going to be a sum.
Unless fxy itself is also 0.
Yeah.
Then you get d equals 0, then it's inconclusive. Yeah. You guys all sort of with me? Okay. How are we doing so far? So this just becomes a construct and throw shit in. Yes? Construct and plug and chug. So negative 2, 1. You still get 0. And who cares? And then minus, and you still get 16, yes? So you get less than 0, so what is happening here? It's another saddle. Which kind of makes sense with most of these guys. You're going to get some symmetry going on, bless you, bless you. And so if I check out 0, 0,
Inconclusive.
0, 0, this would be 2. This would be, this would be 4.
Minus 0.
And this would be 0, yes? Which is 8, which is greater than 0. So d is greater than 0, and fxx is greater than 0, yes? Is everybody with me?
Yeah.
D is greater than 0. fxx is greater than 0. So I have a minimum at, where'd it go? 0, 0. Whew. Let's graph this thing very quickly. Then we'll do number 3. Then I'll say a few quick words about this and then we'll head out. Okay? So let's see. Graph this thing. Wait. What was it? X squared plus 2y squared, yes?
Minus x squared.
Minus
X squared y.
x squared y. Alright, so let's look at 0, 0. What's happening at 0, 0? Did you, what you say? An udder. Or what is it called? A uvula? What is that? The back? Epiglottis? I don't know freaking biology. So that's obviously the min, and that's exactly, is that what we said? Thank God. We said a min is 0, 0. Yes? It's always nice to get verification. And then we said at 2, 1 and negative 2, 1, there should be saddle points. And if you look at, let's see if I can get you guys to, oh God. Okay. 2, 1 is like right there, and there seems to be a saddle point. Let me see if I can see how this way it's up parabola,
Yes.
and this way it's down parabola. Yes, are you guys cool with that?
Sure.
And the same thing happens. This is nice and symmetric. Yes, so it kind of makes sense that those are both the same idea. Those are both saddle points. Okay. So what's really nice is when you're doing your homework, if you're near a computer, especially if you're doing web design, then you're actually on a computer, and then you just pull up Desmos and graph the damn things and make sure that it actually kind of makes sense. Some of the graphs are going to be really weird, so it's not going to be easy to kind of check, but a lot of them you can actually check. From this perspective, this doesn't tell me much, but that looks better. Okay, looks like so many things. Okay. So here's something you guys are going to be very excited about. The minute we learned local maxes and mins, we had some like absolute max and min, but we also had optimization. So does this sound at all familiar to problems you did back in Math 180? Find the shortest distance between the point blah blah and the parabola blah blah blah. You guys remember those kind of problems? Find the largest volume of the box you could construct from this much material. Yes? Huh? Huh? Sorry? Optimization. Yes. You good with that? Okay. So how the shit am I gonna do this?
Don't you need to find like a normal the
Oh, I see. I like this. So you're thinking about normal to the plane and doing stuff with that? No. But I don't blame you. You actually could do some stuff with that, but it would be way more than you have to do. Can somebody tell me the coordinates of every point on the plane?
X plus y plus z equals 1.
That's not coordinates. I want coordinates. So listen. How many variables could you just make up before we had to get serious? What has to be true about all three variable numbers I picked? They have to add up to be 1. How many can you just totally just make up, pull out of your ass before you have to get serious? 2 of them, yes? You guys with me? So those of you in my linear, it's like 2 for your arrows. So if I choose, so what's a point on this plane? X, Y, but now I gotta get serious, yes? I can pick anything I want for X, anything I want for Y, now I gotta get serious. What's the last one have to be then? No?
Oh.
Equal to 1.
I need X plus Y plus this thing to be 1, yes?
X plus y.
So all you have to do is solve for Z.
1 minus z minus 1.
No. Solve this for Z. What do you get when you solve this for Z?
1 minus x minus y.
If I add these 3 up, don't they equal to 1?
Yeah.
Kind of like, of course they do, yeah? So that represents every point on the plane. And a quick side note, my linear people, couldn't you write that as a column? Make 1 as a multiple of x, 1 as a multiple of y, so you have 2 vectors, and that's why it's a plane. Okay. Ooh, whoop-de-doo. Those of you not in my linear, who cares? You're fine. It's just another way to look at it. Does everybody see how that represents every point on that plane? By the way, you did this shit in Math 180. So if I give you y equals x squared, what's every point on that function? X frickin' squared. There you go. That's every point on the function. That is actually another way we could have defined every function. We could have just wrote every function as a point. This could be the equation of a plane instead of this. I kind of prefer this. Mostly because it's what we're used to. Now, what do I do from here? Now, real quick. If I want the shortest blank, or the longest blank, or the biggest blank, or the lightest blank, or whatever, I have to figure out a function for blank. And then what do I do with that function? Find the derivatives, because I want to find the extrema, yes? So whatever the blank is, whatever I'm trying to find the shortest, biggest, smallest, whatever, the minimum, max, whatever the shit, I need a formula for that. So what formula do I need here? Distance formula. Now there's a trick from Calc 1. It's not really a trick. The distance formula has a square root over a whole bunch of shit, yes? Especially in 3 variables, oh my god. So if I minimize the square of a number, doesn't that inherently mean I've minimized the number? especially if the number itself has to be positive. Yes, the only way that could kind of fail is if it could be negative. So can somebody tell me what's d squared? What's the distance squared? How do I find the distance between 2 points? Good. X minus 2 squared. Y minus 0 squared.
Minus
1 minus x minus y minus negative 3. Yes?
Yes.
So this minus that squared, this minus that squared, this minus that squared. What is 1 minus x minus y minus negative 3? It's 4 minus x minus y, yes?
Wait.
Oh, minus.
Minus minus, yes. Oh, the damn negatives. They find a way. Negative and 0 finds a way to screw us over. Let me stop for a minute. Are you guys semi with me? How do I find the distance between 2 points? X minus x1 squared plus y minus y1 squared. What about 3 dimensions? Plus z minus z1 squared. What about 4 dimensions? Plus w minus w1 squared. What about 80 dimensions? Plus stuff squared. Keep going. Yes? That works in any dimension. It's crazy. What do I do now? Take the derivative. We got the function that I'm trying to do shit to. I'm trying to find the shortest distance. Okay, so if I can find a distance function, I can then do calculus to it, attack it with calculus, yes? Now we got a distance squared function, but that's fine. If I minimize it, I automatically minimize the distance. So what's distance squared? I'm sorry. What is the fx? Let me call this fxy. Is that cool? What is fx? It's going to be a little more involved, yes? This first part I'll do. Here we go. Woo, oof, okay. Right? So you're this with respect to x. You can do it.
Oh, minus. It would be minus 2.
It will be, yeah, it will be minus. You're right. But let's see. Take the 2 down
Yeah.
in front of all this business times
Negative
-1.
1.
Chain rule. Yes? Are you guys with me? Once I get the function that I'm trying to find a maximum or a minimum for, I'm trying to optimize. In this case, I want to be as close as I can. I then attack it with calculus. In Math 180, we took its derivative. In Math 281, that's not specific enough. I have to take all the derivatives. Yes? All the first partial derivatives. So I'm not done with my derivatives, right?
Mm-hmm.
I want that to be 0, but I also want fy to be 0. I don't even know what fy is yet.
It's 2y minus.
Yeah, so fy is
2y minus 2 times the square.
2y minus, 2.
Times the square.
So this will be minus eventually, yes? Yeah. Do you guys see how we can do like we did before? If I set these equal to each other, like we did on the other problem? Yes.
Why do you use d squared instead of just d? What is this one?
If I use d, I have to square root both sides,
Okay.
and then the derivatives would be really gross,
Okay.
because then it would be chain inside of a
Yeah,
chain, and
yeah.
oh my god. So that's kind of nice. That just shows you, if you step back from the problem for a second and go, I don't have to get that far, I don't have to drill that far down. If I minimize the squared distance, I minimize the distance. And this is, I'd much rather work with this thing.
Yeah.
Yeah. So if I set these equal to each other, what happens with this piece?
Yeah.
Yeah, so then I get 2x minus 4 equals 2y. Is that cool? So then I get y equals x minus 2, yes? So that line contains all the points that makes fx and fy equal to each other. But I specifically want the points that make fx and fy what, so we want them equal to each other, and they have to be what to find the critical points? Equal to each other and they have to be 0. We made them equal to each other. Every point on the line y equals x minus 2 makes fx and fy equal to each other.
Okay.
You guys with me on that?
But now we gotta test them.
Now you have to figure out, okay, but which specific points, or maybe every point does this. And who remembers how I did that? What do you do now? Plug it in. Yeah, how do you check what you've done to see if it works? Plug it in, see if it equals 0, or set it equal to 0 in this case. So now I take,
Love you guys.
so now I know y equals x minus 2 makes them equal to each other. That makes fx become 2x minus 2 minus 2 times 4 minus x plus 2. Is that cool? There used to be a minus y here, and I replaced it with x minus 2. Okay, so then I get 2x minus 4 minus 8 plus 2x. You could have just, that's good, Jack. Sure, just keep going. So then I get 2, 4, 6x minus 16, it looks like. Which means x would have to be,
Would it be 2x? Oh, never mind, I see what I said.
so what did I do? I took what we knew made the two partials equal to each other and plugged it into one of them. What happens if I plug it into the other one? Same thing, because isn't this what makes them equal to each other?
Yeah.
So if this makes one of them 0, doesn't it make the other one 0? Are you guys all with me? This is the hardest kind of thing you're going to have to do with these. In this case, what does x have to be? You can do it. Nothing, it's not too pretty, but who cares? 8/3, is that cool? Add 16, set it equal to 0, sorry. X is 8/3. If I plug it into fy, I get the same thing. What's y got to be then?
Yeah, 8/3 minus 2.
So therefore, what's the critical point?
8/3 2.
And then how do I check to make sure this is actually the minimum?
You have to take the second derivative.
You can do the second derivative test, yes? Now to be honest, you could actually take a point close to this, plug it into fxy, and show that it's bigger than what you get when you plug this in. That's all you really need. I don't know if that's something else you did in Math 180, but you can just calculate big ass D, yes? Now this actually turns out to be the right answer. You do it either way I just said. Either calculate big ass D and show that it actually comes out to be a min, or plug in a point close to this and show that that results bigger than this makes f of xy. Okay, maybe. I don't know if you guys remember when you first did the number line, remember, and you put your little critical numbers,
0, 1.
and then you said, okay, this is positive, negative, negative, yes? How did I know that this was a maximum? Is because it on this side is up and this side is down. So go, yeah. So if I find a critical number and I plug it in, and then I plug anything around that, and it makes it smaller or bigger, that would be evidence that it's either a max or a minimum. Okay, so that's another way to kind of do this when I have a specific critical point. Or I can just calculate big D. Okay. All right. I think that's enough for today. So, one quick word. This back part is going to be our first little step into double integrals. So kind of like to do it by doing problems from Math 180 using double intervals. So you could have done this back in Math 180, we just didn't want to. You know, like, I still don't want to. I'm like, it's too bad. It's too bad. We're going to. So we'll do the other side of this next time. Anybody not get their test back? Everybody got their test back? Okay. All right, guys. I'll see you Wednesday. Or some of you guys I'll see you later today.